You ever see one of those really tall, skinny white antennas up on a tower and just wonder, what's actually going on in there? How does that simple-looking thing get such amazing range? Well, that's a collinear antenna, and today we're going to crack it open and uncover the brilliant but simple engineering secret that makes it all work.
So really, what is the secret sauce inside that tube? Because I can promise you it is not just a long piece of wire. Nope, there's a super clever principle at play here, and we're about to break it all down.
You know, in the world of radio, the name of the game is gain. It's all about making your signal go farther and come in clearer. And you can't just keep turning up the power knob. The real magic, the really elegant solution, is to make the antenna itself work smarter, not harder.
Okay, so the very first clue is hiding in plain sight, right in the name, collinear. It sounds kind of technical, but trust me, the idea at its heart is actually incredibly simple.
Yeah, collinear literally just means in a line. That's it. We're just taking basic workhorse antennas like your standard half-wave dipoles, and we're stacking them, one on top of the other. But the real question is, why? What does stacking them actually accomplish?
So picture this. A single, lonely dipole antenna sends out its signal in a pattern that looks pretty much like a donut, right? It's pushing that signal out evenly in all directions horizontally, but it's also wasting a ton of energy shooting it straight up into the sky and down into the ground. That's our starting point.
Now here's where it gets cool. When you start stacking these elements, you're not just making a taller antenna. You are fundamentally changing the physics of how it works. You literally start to squeeze that donut, taking all that energy that was going up and down and forcing it out, flat, towards the horizon. But, and this is a huge but, there's a catch. And that catch, my friends, is the real secret of the collinear antenna. See, you can't just slap them on top of each other and call it a day. For this to work, for them to help each other, all those individual parts have to be in perfect sync. And this is a little concept called phasing.
Just think about it for a second. If one part of your antenna is pushing a radio wave out, while the part right above it is pulling back, well, they just fight each other. They cancel each other out completely. And your super fancy high-gain antenna, it basically becomes a dummy load, a glorified resistor that just turns your precious signal into useless heat. No gain, all pain.
The solution is this clever trick called phasing. Engineers stick a very carefully calculated delay line, which is really just a little section of feed line between each antenna element. It's cut to a super precise length that basically hits the pause button on the signal just long enough for the next element to catch up, and boom! Now they're all pushing and pulling together in perfect harmony.
Now, engineers have a few ways to pull this off. Some modern designs, like the ones Ed Fong is famous for, use a tightly wound phasing coil. It creates that delay, but keeps everything compact enough to fit inside the tube. Older designs, like the Ringo Ranger, use what's called a phasing stub, which kind of stuck out at a 90-degree angle. Both can work, but man, getting it right is incredibly tricky.
And this is really where the rubber meets the road. The idea of stacking and phasing, it sounds simple enough on paper, but actually building one that works perfectly, that is an absolute masterclass in precision.
Just listen to the legendary antenna designer Ed Fong. He basically says, "I've tried all the things that don't work so you don't have to." He spent years and years experimenting to figure this stuff out, which should tell you this isn't something you can just whip together in an afternoon and expect it to be perfect.
I mean, just look at this list of what can go wrong. If that phasing coil isn't crushed down super tight, it'll radiate on its own and completely mess up the pattern. If your measurements are off by a single millimeter, 1 millimeter, your performance just tanks. Even the type of plastic pipe you put it in, the radome, totally changes how it works. You have to tune the antenna while it's inside its final home. It is an incredibly precise and unforgiving process.
Okay, so let's imagine you did it. You get it all right. The construction is flawless, the phasing is absolutely nailed. So what did you actually get for all that effort? This is where we hit the fundamental trade-off of any high-gain antenna.
Okay, here's a great little rule of thumb to remember. Every time you double the number of elements you stack, you get about 3 more decibels of gain. Now 3 dB, that's a magic number in radio. It means you've effectively doubled your power. So check it out. You stack 2 dipoles, you get that 3 dB gain. Awesome. But to get another 3 dB, for a total of 6, you got to double it again to 4 elements. And to get to 9 dB of gain, you need 8 elements. You can see how the antenna gets really tall, really fast, and you start to get diminishing returns.
And this right here is probably the most important thing to get your head around. Gain isn't free energy.
The antenna doesn't magically create more power out of thin air. All it's doing is acting like a lens. It's taking the power you feed it and focusing it by squashing that radiation pattern.
Ed Fong has the absolute perfect analogy for this. A low-gain antenna, like our dipole, its pattern is like a big, fluffy donut. A high-gain collinear antenna squashes that donut down until it's really, really flat, like a pancake or even a flying saucer. All that energy that was going up to the sky and down to the ground is now laser-focused right at the horizon.
And this brings us to the key takeaway. Gain is not the same thing as coverage. If you're up on a mountaintop and you're trying to talk to another mountaintop 100 miles away, that flat pancake beam is exactly what you want. But if you're trying to talk to people in the valley right below you, that super focused beam might shoot right over their heads. For that job, you actually want the broad coverage of the donut.
So, now that we know how it works, and we understand the big trade-off, let's bring it all home. Let's talk about how you actually choose the right tool for the job.
Let's make this super practical. If you're setting up a local repeater that needs to cover a wide area, maybe even some people down in a valley, lower gain is actually better. You want that broad coverage. But for that mountaintop to mountaintop link, you go for the high gain to focus all your power. And for just general, all-around use, talking radio to radio, a simple, forgiving low-gain antenna is almost always your best bet.
And here's one last piece of pro advice. For most people, the absolute best bang for your buck is a simple 2-element collinear. It gives you that awesome 3 dB boost, effectively doubling your power, without making the radiation pattern too flat and without the antenna becoming ridiculously tall and hard to put up.
So the next time you're looking at antennas, don't just ask, how much gain does it have? That's not the right question. Instead, ask yourself this: what am I actually trying to do here? Am I aiming for raw distance, or do I need good, solid, all-around coverage? The answer to that question, well, that's going to tell you everything you need to know.